Okay, so today we're going to be looking at topic 8, block 1, and this is on page, give me a second here, page 233 in your math book, page 233. All right. So leading into this, Terrence is teaching his friend Teresa how to ride a skateboard. To help her practice her control of the skateboard, Terrence uses a special drill. As Terrence balances on the as Teresa balances on the skateboard, Terrence pulls the board in a straight line at a steady rate. So, as Teresa balances on the board, Terrence pulls the board in a straight line at a steady rate. And when he does that, this is the graph of the data that we get from the motion detector. Okay. So, how did you decide where? So, how do we decide where Teresa should begin the skateboarding? So, how do we know where she started? Can anybody tell me that? How do we know where she started on this graph? What was her distance from the motion detector? If you notice at the very beginning where we were looking at time down here, right? When the time was 0, how far was she from the motion detector? Okay. Well, it looks like definitely less than 1 foot, maybe 7/10 of a foot. I don't know, but definitely less than 1 foot, slightly less than one. Right. Because when we look at it here, we can see that when we are at 0 seconds, we're just almost 1 foot away from the motion detector. Okay. But then what is true about the rate that he dragged the skateboarder to make this line of data? What can you tell? Can anybody tell me anything about the rate? Is it a fast rate? Is it a slow rate? Is it a constant rate? Is it a rate that varies in speed? Anyone out there feeling brave and bold and scholarly? To me, it doesn't look like she's going super fast or super slow. But because we've got a straight line, right? Because we have this straight line, it is definitely a constant rate, right? We can definitely agree that the skateboarder is being pulled at a constant rate. And that's important because if you don't have a constant rate, you're not going to have the straight line. Okay. So let's go on to the next question. Now, this one says it's a reinforce. For each graph, identify how far the skateboarder was from the motion detector. Okay. So at the beginning, right? Initially, how far was this skateboarder from the motion detector? Initially is the word. Okay. This is block 8. Yes. Sorry, no. Topic 8, block 1. Topic 8, block 1. In case you're still fishing around. You don't have it. Okay, just is that because you don't have your math book yet? Is that why? Okay. So give me a second. Well, okay. So for now, Manveer, could you just agree to just kind of take notes, and I will figure a workaround for you and let you know. Okay. I promise. All right. So, but I definitely wanted to try to get you the math book as soon as possible. So thank you, Annika. Yes, the skateboarder starts at 1 foot away from the motion detector, right here. Why isn't it letting me draw? Come on, there we go. Okay. 1 foot away from the motion detector. All right, so let's continue on to the next one. In this graph, what is the distance from the motion detector at the beginning? So we can go here and we can find that, right? It's right there. 3, when at 0 seconds, the distance from the motion detector is 3. All right, very good. Yes, thank you. And in this one, when the time is 0 seconds, how far from the motion detector is this skateboarder? Come on. There we go. Looks like 7 feet, right? At 0 seconds, we're at 7 feet from the motion detector. Now, that part is really going to be very important as we begin to take a look at questions regarding graphs of lines. And so we want to make sure that you are becoming familiar with when the x, right? Because we have our two axes here, right? We have the x-axis and the y-axis of our graph. And when x is 0, where our line crosses the y-axis is going to be very, very important. Okay. So now the thing that you need to know is that when a line crosses the y-axis, all right, so when it does that, when we cross the y-axis, the y value at that point is technically, and mathematically, we're going to use the correct term, is called the y-intercept. And well, that's because that's where the line intercepts or crosses paths with the y-axis. Okay. And then another part of a graph when we're looking at this stuff, when you're looking at graphs of lines, the measure of the steepness of a line is going to be called, and you probably already know this, is called its slope. The slope is the measure of the steepness of a line. Okay? Now, when we take a look at question number 5 here, we're going to calculate the rate of change by analyzing the differences in the y values and the differences in the x values. Okay? So you can see from this table right there that as x goes up by 1, right? 1, 1, 1, 1, 1. The change in x is 1. How much is the change in y? How much does y change as x changes by 1 every time? So you go from 0.7 to 1.1 to 1.5 to 1.9. What is the change in y? Thank you. Yes, 0.4. And it would also do the same thing in the graph. If the graph was a little more detailed, we'd be able to see that every time x goes up by 1, or sorry, when x goes over by 1, it goes up 0.4. Over 1, 0.4. All right, every time that it goes over 1, it goes up 0.4. So the change in y over the change in x is 0.4 over 1, which of course is just 0.4. And that is our slope. The rate of change, not slope, sorry, the rate of change is the same thing as slope. Rate of change is slope, and that's very, very important. Okay. Oh my gosh, it is 10:24. I am officially out of time. So, hold on a second here. Let me